Hi, everyone. I'm just getting everything in order. If you might be getting messages from other students who are not able to join. If so, please send them a link to the YouTube stream, which will be a temporary measure. I'm just getting everything in order. See. If you might get. Yep, sorry about that. So just give them a link to the YouTube stream in case they can't get in. And that'll be a temporary measure just as we get everyone enrolled properly and ready to get the Zoom links. Just waiting for Matt to join as well. All right, hi everyone. Just checking if Matt is here. Matt Coster. Okay, if not, that's fine. We can go on without him. All right. Okay, so welcome to MAT240. So today is September 8th, 2022, and this is the first class of MAT240. This is a course which is usually called Algebra 1, and it focuses on linear algebra. It's an advanced linear algebra class. Okay, now, so I got normally I have the TA present here. That's why I'm normally not having to deal with these issues, but okay, fine. So there's a couple of things I want to say before we begin. Okay, so the first thing is that it may seem a little strange that this class is being offered online. Okay, so this is a very large class. Right now we have 300 people. Normally it doesn't stay that large, but it's still going to be large in the end. And the planning for this class starts far in advance of the date, of the dates of today. So even last year we were already planning this class, and so the plan originally was to have it online. So I was asked to teach this online in case that the pandemic would continue, and so that's the reason that it's still being offered online. Now, although the lectures are online, the tutorials are in person. The TA office hours are in person, and the term exam is going to be in person, and the final exam will be in person. So the only component of this class that is online is the classes and the office hour for me, not the office hour for the TAs, just because the office hour for me is connected to the Tuesday class. All right, now, okay, and the first kind of official statement is about the syllabus. So let me share the syllabus. 1 second. All right. So this is the syllabus that you should have gotten on Quirkus or from the class webpage. The class webpage is accessible through my webpage, mgwalt, in the courses, and it's at 240. So the class webpage, you can download the syllabus from there, or you can get it from Quirkus. So my name is Marco Gualtieri. I'm a professor in the math department, and my research area is mathematical physics and differential geometry and related issues. The TAs for this class are these 4 people: Isabel Beach, Samprit Ghosh, Matthew Koster, and CU. Okay, and they're going to be running the 4 tutorials that you should have already been enrolled in. All right. You can read through the course overview. The official textbook is this book called Linear Algebra Done Right. Although I will not be teaching directly from the book. The book is really for the purpose of reading. So it's about training you to read. And I'm going to follow the book closely, but with a different presentation. with a different style of presentation. So the assignments and the reading and the classroom material are synchronized, mathematically synchronized, but they're different, kind of all different. So you can read through all of this stuff, but what you'll probably be most interested in is the evaluation scheme. So there's going to be assignments, 10 assignments, equal value, and the lowest 2 marks will be dropped. And there will be an in-person term exam for 20% and an in-person final for 40%. So this is pretty standard. So it's kind of important with a large class like this that we, try to accommodate people who will not be able to hand in assignments for whatever reason. It could be for illness reasons or for any other reason. So it's for that reason that we drop the lowest 2 grades. Although in practice, for this class, a lot of people end up dropping the first assignment because they really just are trying to get their bearings, and they usually you don't do very well on the very first assignment because you're kind of freaking out, and it takes a while to get into the rhythm of the class. But in any case, for whatever reason, it's taken care of by dropping the lowest 2 marks. So I don't need any. There won't be any term work accepted after the deadline under any circumstances at all. Okay, and be careful about the dates for the term and final exam, and make sure that you prepare for those dates. And if you know that you are going to be missing, or if you won't be able to attend them, then well, read through this and see what you're supposed to do. Okay, and you should read through the rest of this. I'll talk more about academic integrity later when I send you the first assignment, which I'll send you by the end of the week. And then the other important thing on the syllabus is this. I hope to stick to this plan. This is just a plan for when the assignments will be due. So the way that it's organized, I don't remember exactly when the ad drop date is. It's somewhere around 13 November. It's approximately there. So by the time that the ad drop date comes around, you will have had a certain, you will basically have a good picture of how you'll be doing in the class. So that should help you to decide if you want to drop for technical reasons. Okay, so that's all I really wanted to say about the syllabus. And what I'll do is I want to really get into the material right away. So sorry for not. I will discuss with you and ask for questions as we go along. But for right now, let's just launch right into it. Okay, so the main point of this class, okay, is to basically train you in a certain technology, in a certain way of thinking, okay, which is extremely fundamental for all branches of mathematics and physics and engineering and music and so on and so on and so on. It goes under the name linear algebra, but it's also fundamental to quantum mechanics, even to Newtonian mechanics, to data processing, statistics, chemistry, you name it. It's a kind of universal kind of tool that you can use to study systems and their interactions of all kinds of different ways. There seems to be no end to the variety of applications that you can make from these tools. And this layer of software, if you want, that you need to install in your brain in order to continue in mathematics, okay, this layer of software is kind of built upon a lower level of thinking, which is what I'm going to talk about here, right now, in part one, namely the topic of finite sets. Okay, so as far as I can see, this is kind of the core kind of assembly language, or basic foundational thinking that will inform the whole set of things that we're going to discuss for the rest of the class. Okay, so that's the reason that I'm doing this. So this is the basis of everything that's going to come later. And on the other hand, this is not a class on set theory. So I don't want to get into the details of set theory as a subject in and of itself. Okay, so I'm just going to try to introduce in a very kind of minimalistic way the basics of sets that we need to continue. So what is a set? So a set I'm only going to describe it in a very loose way. So it's a collection of objects and this collection is viewed as an object in and of itself. That's how you should think about it. So it's like you take a collection of objects, you place them in a container in a sense, and you call it a set. And then that set can be an object which maybe is an element or is part of yet another set. Right? So you could have the set of people in this class. So we could call the class MAT240. You could think of it as a set containing its students, its TAs, and its professor. And that's that entire set, which we could give the name MAT240. It itself is a member of a yet larger set, the set of all classes at U of T, let's say, right? And so you could think of U of T, right, as a set containing all of the classes, right? And each class itself is a set containing all of the students and all of the people, right? So it's a kind of somewhat recursive idea when you first encounter it right off the bat. It's kind of recursive in the sense that there's no reason why a set cannot be an object inside another set. Okay, so when so let's give a set a name. So if S is a set, and X is an object in S, we write, so this is the first piece of notation that you're going to encounter. So we write that X is an element of S. That little epsilon, it kind of looks like an epsilon in the Greek alphabet, simply means is an element of. That's how you would read it in English. Okay, so let's give some examples of this concept. Okay, so the simplest kind of set that you could possibly have is one that has no objects in it at all. It's called the empty set. That'll be example 0. So it doesn't have anything in it. Okay. Another example would be, I'll call it P. And I'm going to define this set in the following way. What I'm going to do is I'm going to use this notation where you use these curly brackets. I'm sure that many of you have seen this, but don't worry. Someone has their mic on. Please mute yourself for now. So this is a set containing 3 letters. And look at the way that I defined the set. Okay, I defined it by giving these curly brackets and then listing the elements R, G, and B with commas in between. This means that this is another way of saying that P is the set containing 3 elements, R, G, and B. Okay, now the important thing about this notation right off the bat is that although it is presented to you as a list in order, okay, order is not part of the concept of a set. If you look at the definition, it's simply a collection of objects. It is not a collection of objects in a particular order. Okay, what that means is that this set P, I could have defined it in this way as well. And this would be identical to the first way of describing it. Okay, and the other thing about it is that it might be that when listing the elements of a set, it might be that in your list you happen to give a repetition. So you could do something like this: R, R, G, B. Okay, and the fact that the element R occurs more than once in your list of objects is also irrelevant. The question is simply, what are the elements? The only elements are R, G, and B. All right, so I'm just showing you by example how this particular notation for constructing a set works. Okay, this is a particular way where you just list them all out, the elements of the set. Okay, let's do another example, a set that you are very familiar with. It's the set Z with Blackboard bold font. Okay, it's called the integers. It contains all whole numbers, whether they're positive, zero, or negative. And here you find another piece of another typical notation where people write 3 dots because you're supposed to understand the pattern and continue it forever. Okay, the set of integers. Again, I happen to list them in order. The order is kind of useful in order to make sure that you list them all, but it's not part of the structure of a set. It's just, the point is that it contains all of the integers, and that's all. I could have listed them in the opposite order. I could have permuted them in an arbitrary order. It's irrelevant. And let's continue. So there's other sets that you're very familiar with. You know that when you are introduced, I mean, normally you're introduced to the counting numbers 1, 2, 3, then you're introduced to the concept of 0, which is a number that if you add it to any other, it doesn't affect it. Okay, and then you are introduced to the concept of negative numbers, but then shortly after you're introduced to whole numbers, you're introduced to the idea of fractions. So there's this formal construction, which you're very familiar with, of the rational numbers. Okay, and here we introduce another level of notation. So a rational number is always looks like a whole number, a line, and another whole number. So really, a rational number, you could think of it as being specified by a pair of integers, p and q. And then I'll put here these two dots, okay, which just mean such that. Oops, that's not a very good color. So p is an integer. And so I can put the condition that the symbol p is an element of z, and therefore it is a number. Okay, and that's a possible numerator for a fraction, as you know. But the denominator is not any number. It can be any number except 0. So p is in z and q is in z, but where we remove a single element from z, and that's the notation for that. So this means the set z remove the element 0. Okay, and so this is I'm giving these examples not just because they're examples, but because they're examples of constructing sets using notation. And this notation is the such that notation. You basically are able to provide a kind of list, an abbreviated list, okay, and then you put conditions. You place conditions on the quantity that you're including in the set. So p has a condition that it's a integer, and q has a condition that it's an integer that is non-zero. Okay, and you could list several conditions. Here's the first condition, here's the second condition. I could put a comma and place many more conditions. And I could use this method to define the set. Okay, and then you also are aware of a more sophisticated set called the real numbers. And the construction of the real numbers is very interesting. We're not going to talk about that in this class, but you will have analysis classes, and you probably already saw something about how the real numbers are constructed. But you could think that the way that the real numbers are constructed is as sequences of rational numbers. Because you could think that, based on your intuition about real numbers, you know that every real number can be described as a sequence of approximations, each approximation being a rational number. And so you could say that the real numbers consists of sequences of rational numbers with a certain property. Okay, so these are kind of convergent sequences of rational numbers. So there is a construction which starts with the rational numbers and produces as the outcome the real numbers. And I'm not going to go over the construction, but it's an outcome of the rational numbers. And then another example that we are going to discuss in this class is the complex numbers. And these are yet more sophisticated examples of sets. Okay, so these are just a bunch of examples of sets, and let me continue defining this concept. So we say that a set S is finite and again, this is a very simple idea if it has a finite number of elements. Okay, this number is called the cardinality of the set. And it's denoted by these bars, bar S. And this cardinality, what is it? It is itself an element of a set. And what set is it an element of? It's the set of numbers from 0 to infinity, not including infinity, just. Okay, so every finite set has a cardinality, a size, a number, okay? Okay, so this is the concept of what a set is and what it means when we say that it's a finite set. Okay. Any questions about this? If you have a question, then raise the hand using the feature there on where is it? Well, you know how to do it. So, Ibra, go ahead.
So I have two questions. The first one, in the example you gave, number 1. So does the third one in set P, does that still count as set P even though the R is repeated, or is that a different set?
That's the reason that I gave this example. It's to show you that you can list, the purpose of the list is to simply indicate G is an element of the set. G is an element of the set. R is an element of the set. So the question is, what is an element of the set? G, R, and B are all elements of the set, right? It's a list of true facts. If you list a true fact twice, it's still true.
There's at least one R, one G, and one B in this set. That's what it means.
No, this is a complete specification of what the elements of the set are. The set contains 3 elements, R, G, and B.
Okay. And what does cardinality mean again? I didn't get it.
Read what I wrote. Read what I wrote.
I did. Okay.
This number, the number of elements in the set, is called the cardinality. So example number 1 has cardinality 3.
Oh, okay.
All right.
Thank you.
Number 2, example number 2, it has an infinite cardinality. It does not have a finite number of elements, and so it is not a finite set. On the other hand, example number 0, it has cardinality 0. It has no elements in the set.
Okay, thank you.
You're welcome. Nora, please go ahead.
Oh, I just feel unclear for the notes about question 3, and the set Z removes something. I just not clear about that. The question
So
3.
this is a notation. Okay, this notation.
Yep.
Is simply taking a set, okay, and saying that this notation simply means all of the elements of Z, but not this element.
Oh, okay.
So it's a way of removing elements from a set.
Oh, okay. Got it. Thank you.
You can think of this as like a minus sign. Sometimes people write it like this. Okay, but the more common notation is with a slanted line.
Can I put the empty set inside?
Let me leave it there, and we're going to get more into sets, okay? But I'm not going to answer all of the questions right now. So I'll take one more question. Jerry, please go ahead.
Oh, hi, can you hear me?
Go ahead.
Oh, can you please clarify the difference between the object and element?
There's no difference. They're the same.
All right. Thank you so much.
You're welcome. Okay, let's move on. Okay, so right now I've introduced, okay, so this is very important. And for those of you that are still asleep, you should wake up for this moment, okay? And that is that when you introduce a new concept in mathematics like this, like the idea of a finite set, okay, it doesn't, it's like there's two parts of the recipe. There's 2 parts of the idea, always. There's what the concept is, what the idea is, okay? And then there's also the relationship between versions of this idea. So always, when you introduce something, okay, this is incomplete. If I only tell you what an object is, right, I haven't done my job yet. I'm not finished, okay? You need to explain how these types of objects relate to each other. It's a very important idea, okay? Let me explain what I mean. So it's kind of like when you buy a device, okay? When you buy any kind of electronic device, the electronic device by itself is inert. It doesn't do anything. It's just a piece of matter, and it has no functionality. But the way that the functionality comes about is by connecting it with other things, plugging it into the wall or putting a battery into it, connecting it via Ethernet or via Wi-Fi, and so that they can communicate with each other through protocols, right? And that's what allows the nodes of a network to produce, to make a network, right? To make a structure that is somehow more than the parts that it makes up. They need to relate to each other. And right now we're in a situation of having introduced finite sets, and these finite sets are just kind of floating in space and they're doing nothing, okay? So in order to be able to do something with them, we need to explain the concept of a map between sets. So that's the second important idea. Okay, now the concept of a map is extremely simple, okay? And it is very close to what you have learned in high school as being a function. So map is a synonym of a function, but function is usually used in a much more restricted context. So you could say that map is slightly more general than function. Okay, but it's the same idea, okay? And even people who are very familiar with functions, they will often get confused when talking about maps in general when you first see it. But this idea of a map of sets is something that you really need to get clear in your mind, okay? So what is a map? Let me explain. So suppose that X, so a map is always, it always goes from somewhere to somewhere else. A map has a direction. It has a preferred direction. It has a beginning and it has an end. From a set X to a set Y. And this set X, when it's the from space, when it's the from set, we call it the domain. And when it's the to space, we call it the codomain. Okay, now, with all of these things, there are synonyms that are sometimes used, but let's not confuse, I don't want to confuse people by giving all of the synonyms that have been used in the past, sometimes in the very distant past, in the 19th century and so on, for all these ideas. So just stick with the modern notation and we'll be better off. So whenever we have a map, you need to focus in your mind on what is the domain of this map and what is the codomain of this map. That's first. That's what you think of first. Where does it go from and where does it go to? And then the question is, what does it do? The map, so a map F, and I'm going to use the notation that it's a very descriptive notation that goes from X to Y. So this is just the notation that we use to depict the map. The reason that this is useful is because it shows you what the domain is and what the codomain is, because it's the tail of the arrow and the tip of the arrow. Okay, so you can, so this map, what does it do? It sends each element of X to an element of Y. Okay, and this element, so in other words, for each X in X, the map F sends it to an element which we call F of X in Y. Okay, so it takes an element of the domain and it assigns to it an element of the codomain. Okay, it always goes in this direction and not in the reverse direction. Okay, it has a very strong directionality to it. Okay, and what we write to indicate that X, little x, is sent to F of X, we write it in the following way. We say that if you have a map from X to Y, we write it this way. And if you have an element of X, I'll write it in this way. This is to indicate that X, little x, is an element of big X, and it will be sent by this kind of arrow to F of X, which is an element in Y. So this is a very subtle notational change where we put a little bar on the tail of the arrow to indicate that this is what the map F does to an element. Okay, so sometimes it's also, maybe it's useful to write it this way. So F, we can label it with F just so that we're clear what map we're actually considering. Okay, so this is just the notation to depict what the map is doing. Okay, so let's look at some examples of this. So, for example, you might be familiar with the RGB system for colors on your computer, an Rgb Color. Okay, what is an Rgb color? Well, you know that when you're looking at a photo, let's say on your computer screen, every pixel of the photo is assigned a color by giving three numbers, three integers from 0 to 255. So there's three of these numbers indicating the amount of red, the amount of green, and the amount of blue in the pixel. And then the three LEDs in your computer screen will illuminate, at those intensities in order to produce the color. So if I wanted to identify a particular color, right, what is that color going to be? Well, it's going to be it's going to have, it's basically specified by three numbers, one for R, one for G, and one for B. So you could think of it as a map. It's a map. C, which goes from the set R, G, B, which you could just think of as three letters of the Roman alphabet, okay? And this map will assign to R, to G, and to B a number in the range from 0 all the way to 255. So so we have a set of cardinality 3 as the domain. We have a set of cardinality 256 as the codomain. And a color is exactly the assignment of a number for each of the three inputs in the domain. So, for example, black is a map. The color black is a map that takes R to 0, G to 0, and B to 0. Okay, so that's an example of a map. The color is a map. The color black is one of the possible maps with this domain and that codomain. Now, without changing the domain and without changing the codomain, you could have many different maps. Another one would be white, which is a function or a map. You could call it either way. A map taking R to 255, G to 255, and B to 255. Okay, and so just continuing this example, going a little bit further, okay, what I could do is I could use this idea to define a new set. So we can, example 1 continued. Let's use this idea to define, let's define a new set from the old ones. What I mean is from the set Rgb and 0 up to 255. Okay, I'm going to define a new set. This will be a set I'll call M, or actually, let me call it curly C. And this will be the set of maps. From P to 0, 1, up to 255. Okay, so now what I've done is I've taken, now that we know that a specific color is a map from P, this is P. A specific color is a map from P to this set of numbers from 0 to 255, right? And now I'm going to collect all such maps, all possibilities, into one set, the set curly C, and this is the set of all possible RGB colors. Okay, now the question might be, you might ask, based on what we've introduced so far, you might ask whether, you might ask how many colors are there in this system? How many maps are there? Well, that's fairly easy to discover, right? Because you could just imagine how many different ways can I build a color? If I need to build a color, I need to assign 256 possible values to the first element R, another 256 for G and for B. So that means that there are 256 choices for each of the three colors, for each of the three components of the color. All right? And so that means that this set has a cardinality, which is, well, what is the cardinality? The cardinality is basically how many possible ways are there to assign 3 of these numbers to the 3 colors that compose the final color, and that's going to be 256 for the numerical value of R, multiplied by 256 for the possible numerical values of G, and multiplied by 256 times the value of B for the possible values of B. And so you get a finite set of cardinality 256 cubed. Okay, so here I'm just taking the opportunity to construct another finite set, much larger, starting from 2 fairly small sets, one of size 3 and one of size 256. And so this is an example of how we can use the idea of maps. Okay. The other thing I should say is that you've already studied many types of maps already. So example number 2, that you're already familiar with many maps. And these are maps with domain, the real line, and with codomain, the real line. This is something that high school math focuses on bizarrely strongly. I mean, they're like obsessed with maps from R to R. Like that's basically what the entirety of high school math is all about. For example, the map which takes an element of the real line to f of x, which you might be familiar with it in this way. So like ax squared plus bx plus c, where a, b, and c are fixed elements of R. Okay, so this is a map taking every real number. For every real number, it assigns something in the codomain, another real number in the codomain. Okay, and it's very important that this has a direction, right? That the first copy of the real line is treated differently as from the second copy, right? The first copy of the real line is treated as the domain. The second copy is treated as the codomain. Okay, and it's going really from the first to the second. That's an important idea. So it's often the case when the codomain is R or C, we tend to call map a function. It's more common to call such maps functions. But in other words, when a map has numerical values, we tend to call it a function. But you could be mapping, elephants into a gymnasium, right? And you wouldn't normally call that a function. You would normally call it a map. Okay. You could be mapping cars onto a ferry boat, okay? And you wouldn't call that necessarily a function on the set of cars. You would really call it a map from the set of cars to the boat. Okay, and when you have such a function, we also display the function as a graph. A graph is basically a lookup table. So what do I mean by that? I just mean that you usually draw this type of picture, which goes back to Descartes. Okay? And this picture is a picture of the domain and the codomain at the same time. Let me just label it here. So this would be the domain. This line is the domain. And this line is the codomain. Okay, and then what you do is you say that for every point x in the domain, you specify where in the domain, where the function or where the map sends that point into the codomain. So if this is where f of x is sent in the codomain, then what we do is we join them up like this and draw a point of the graph. I'm sure that you're all very familiar with this. And you can draw the graph of all of the values that the function takes on. Okay, and the way that you're supposed to read this graph is that you're supposed to range, or you're supposed to go over all possible points of the domain, and then you're supposed to follow the vertical line until you see the value that the map takes for that input, right? So these are, domain is another way of saying input, and codomain is basically the output. Okay. Okay, so what we're going to do next week is we're just going to really expand out and talk about the properties of these maps and what structure the sets and the maps together form. They form a category. And that's when you should be comfortable. You should be comfortable when you know what the basic components are and how those basic components are related to each other, how you can map one basic component, namely a finite set, to another basic component. So it's always these two things. So that's what I wanted to introduce in this first lecture, is basically the main players, the finite sets, and the main relations between the main players, which are the maps. Okay, so what we're going to do is study those. We're just going to study the category of finite sets, in which the objects are finite sets, and the morphisms, as they're called, are the maps of finite sets. Okay, and then we're going to, once we have studied that, and it'll take us about a week to do that, then we'll upgrade everything. We'll upgrade the main players so that they're not just finite sets, but they're more complicated objects, which will become what we call vector spaces. And then we're going to upgrade also the maps between finite sets so that they become linear maps of vector spaces. And then we will have introduced the second category that we're going to be working with, which is the category of vector spaces. And there is going to be a very strong analogy between these two levels, the level of finite sets and the level of finite dimensional vector spaces. So anyway, for the next week, week and a half, we're going to deal exclusively with finite sets. And then we'll do the upgrade and we'll continue with that. Okay, so that's the end for today. Be patient with the Quercus and the utor ID and all of that stuff. I understand that it's slow to get set up, but you should be ready next week for a more normal proceeding. If there's any questions at the last in the last couple of minutes, please go ahead. But that concludes the class, and I'm going to stop the stream.